Hi there, and welcome to our Chapter 2 problem solving video. In this video, we're going to go over a few 4 or 5 problems, as well as the challenge problem that you can expect on your exam for Exam 1. We're just going to go through every major type of problem that we want to be concerned with in Chapter 2. So the first thing is we want to be comfortable with scientific notation, so we're going to start out there. Just a kind of note, you guys should try to pause this video, answer them ahead of time. I'll work through them one by one. If you want to watch me go through this first one, it's pretty easy. Then you can kind of see how the format of the video is going to go. But I'll present the problem. I'll work through them one at a time. You guys should try to work ahead of me and use this to check your answer. If you really don't know, obviously have me show you one or two. Do it yourself. But we're going to start with scientific notation. So just a reminder on scientific notation is we keep all of the significant figures. So in number A, or letter A, these trailing zeros that are just placeholders that are not significant, we'll cut those out of the scientific notation. We want the very first digit to be in front of the decimal place. All the remaining significant figures after the decimal place times 10 to the whatever exponent based on how many positions we had to move the decimal. All right, so for our first one, since we're going to cut off these three digits, we're going to keep 3.9371, all of the significant figures. Since we moved 3, and then another 3 for 6, and then one more positions for the decimal, we'll have 10 to the 7. Since 300,000 or 39 million is larger than 3.9, we're going to have a positive exponent or increase the number on the exponent. Hawaii, 1,400,041. We're going to convert that to 1.441 times 10 to the 6. These last three zeros are just placeholders. They're not significant. They don't hold any information for us. So we're just going to get rid of them. We move 6 places, 3 and then 3. So we're making the number smaller. We'll make the exponent larger. Again, 19,415,000 for New York. We're going to get rid of all those trailing zeros. They're insignificant. They don't hold any information. Keep all of the significant figures. One number to the left of the decimal, every other number to the right. However many digits we have to move the original decimal to the new decimal is the number we put here. If we move to the left or if we make our number smaller, we'll have a positive change. If we move to the right, which we'll do in the next couple examples, or make the number larger, we'll have a negative exponent. So the last one with the positive exponents, Wyoming's population, the smallest of them, 5.82, we'll get rid of these insignificant zeros. Since we move 5 positions, 1, 2, 3, 4, 5, we made the number smaller, our exponent will be a positive 5, or a change of 5, increase of 5, however you want to think of it. All right, so kind of going the opposite way, we're going to look at numbers that are smaller than 1, or will have a negative exponent on the exponential term. So in this case, we're going to cut out all of these leading zeros. These leading zeros are just placeholders. They don't hold any information. They're just telling us how far we have to go until we do have some actual significant figures, or until we actually have some information that's worth caring about. So we'll go to the first one. Since we have to move this decimal place 11 numbers to the right to get the decimal behind the 7, we're going to have 10 to the minus 7. 7.4 is much larger than this very small decimal. So miles. So instead of using this decimal, we could use this scientific notation, moving till the decimals after the first significant figure, retaining the rest of the significant figures. So we get 1.58 times 10 to the negative 1, 2, 3, 4, and 5. So we moved 5 positions, so the absolute magnitude of the change will be 5. Since we made the number larger, we need to make the exponent smaller. 0.0000158 is much smaller than 1.58. So in order to compensate for that change in the numeric term, we have to decrease the exponential term. So wavelength of red light, about what we would call 600 nanometers, or this many meters. We could rearrange that as 1, 2, 3, 4, 5, 6, 7 places to the right. So we're increasing this number by 7 orders of magnitude. So we're going to times 10 to the negative 7th. All right, human hair, about 15 micrometers, I think. So we'd move 3 to the right, 1, 2 more gives us negative 5, or a total change of 5. Since we're making the number larger, we need to make the exponent smaller, so it'll be a negative 5. All right, so the next one we're going to work on is significant figures. I've kind of been talking about it, pointing out which figures are significant, which ones aren't significant. Now, instead of just identifying which figures are significant, we're going to round to a specific number of significant figures. So we always want to start to the left and move to the right when we're counting significant figures or rounding significant figures. So with number A, or letter A, we're going to count 1, 2, 3, 4. However, the issue with this one is if we use this 8 to round, that's going to bump this from 9 up to a 10, which turns this 5 into a 6. So if we happen to be, our last digit that we're confident is in a 9, and we do round up, it's going to change the number, a little bit more. So our proper answer would be 256.0, ensuring that we maintain, a proper notation for how many significant figures we're confident about. So this one, you could do it either in the formal, just plain decimal notation, or you could put this into scientific notation. It might make it a little easier to read for some people if that's what you're more familiar with. Either answer is correct. Again, all of these leading zeros are insignificant. And then we have 1, 2, 3, 4. We're going to keep this 3, and we use the 2 to determine how we round. 2 is less than 5, so we round down. All right, so now we already have a number in scientific notation. Since it's in scientific notation, we know that every single number in there is significant. We could try to write this as a decimal, but it's already in scientific notation. We might as well just keep it in that format. So we'll go 1, 2, 3, 4. Look to the next digit. 8 is larger than 5, so we'll round up to 2.901 times 10 to the minus 4. Our last one, we have all non-zero numbers, so they're all significant, but we have much more than 4 numbers, so we'll just count 1, 2, 3, 4, and then we'll use this to round. 4 is less than 5, so we'll round down. All right, so now we're going to move into some conversions. Conversions are going to be very important for chemistry in the long haul. So we want to make sure that we get these more than anything. Significant figures, we're going to be concerned for the unit exam that's upcoming and the final. That's about it. Conversions are going to be every single chapter, essentially. There might be 1 or 2 chapters here and there where you don't have to do a unit conversion, but essentially they're always there waiting to happen. So we're going to start with kilometers per day. Now you can choose to either convert the days or the kilometers first. Or, if we're looking up here, we can convert the miles into kilometers first, or we can convert the hours into days first. I'll typically convert my unit in the numerator just because that's my, tendency. So looking at this first one, like I said, I'm going to start with converting the unit on the top. So from miles to kilometers. Again, you might not be familiar with these conversions. I will always give you the conversions. It's useful to know your metric conversions, but I will always give you these awkward conversions like miles to kilometers. I'm not going to tell you how many hours are in a day or how many minutes are in an hour. You're all adults. If you don't have that one figured out, we got some other things that we should address first. So if we multiply 65 by 1.609, we'll get some big decimal. Remember, we're going to keep extra sig figs. So In here, I only have two significant figures, so at the end of the day, I'm going to round this to two sig figs. So really, the right answer would be 1.0 times 10 to the 2, or 100 with two significant figures. However, I'm going to keep some extra decimal places just for the accuracy of the calculation. Now that I have my top unit correct, I have kilometers, I need to convert hours to day. Well, there's 24 hours in every day, so our hours will cancel out or multiply by 24. We'll get some decimal, but we're going to round that decimal to two significant figures, and we'll get 200 or 2,500 kilometers per day. All right, for the next one, converting to feet per second, we're going to do the same thing. We're going to convert to feet first. So there's 5,280 feet in a mile. Again, that's a non-standard conversion that I don't expect you to know. Miles will cancel out, and we'll be left with, 3 million or 300,430 or 343,200 feet per hour. But we don't want this in hour. We want it in feet per second. So what I did here is I calculated how many seconds are in 1 hour. Typically, you might do this through how many minutes are in an hour and how many seconds are in a minute. So 1 hour and 60 minutes, 1 minute and 60 seconds. You could do that, or you could do the combined conversion like this. For the sake of brevity, I use the combined conversion where it's 60 times 60 is just 3,600 seconds per 1 hour. So at the end of the day, we still only have two significant figures, so we're going to round to 95 feet per second. All right, moving to meters per second, we're going to have a similar conversion for distance as we had in the first one. Instead of 1.609 kilometers per mile, we'll have 1,609 meters per mile. Again, we'll keep all of the extra digits that we don't have significant figures for, only have two sig figs here. Here we would have 6 sig figs. We'll keep those just for intermediate calculation accuracy. We'll use the same conversion as before from hours to seconds. We'll round down to our two significant figures, and we'll get 29 meters per second. All right, final one. Again, any weird conversions like this, I'll give to you. So there's 1,760 yards in 1 mile. If we times 65 miles by that, we get rid of the miles and we end up in yards. So we get 114,400 yards. That divided by 60 minutes or times by 1 hour per 60 minutes. We'll round to two significant figures because we're starting with the same number. We always will have two sig figs. So we get 1,900 yards per minute. Kind of a weird calculation, but that's what it is. Alright, so we're going to look at this last back of the chapter problem. So this one involves density. So we're trying to figure out what the density of a sample of glycerol is in given units. So grams per cubic centimeters. However, we're given liters. So that should be the first thing, is that somehow I have to turn liters into cubic centimeters. Now, hopefully we remember that 1 milliliter is equal to a cubic centimeter. So really what we have to do is convert liters into milliliters, and then milliliters is just equal to cubic centimeters, or we do a 1-to-1 conversion. And then we have the mass of glycerol. So if we remember, density is mass over volume, or mass divided by volume. That's the formula. So we have a mass, we have a volume. So we have a density, we just don't have it in the proper units. So our goal is to get it into the proper units. So what we're going to do is, you could do this in a couple different ways, but I think the most direct way is to take 2.5 liters. I am missing a sig fig here. I apologize with that. We should have had 3 significant figures here. I translated it wrong. I apologize. So we would have rounded this to 1 more significant figure. But without that mistake, let's just go through this. So we have 2.5 liters times 1,000 milliliters per 1 liter. Liter is on the bottom. It cancels out with the liter on top. We're left with just milliliters. And then we can do our obligatory 1-to-1 conversion from milliliters to centimeters cubed. A cc is a cubic centimeter, so just to remind us there. So if we were to round this to 2 sig figs, we'd get, exactly 2,500 centimeters. So we still get the same number even though we're rounding to sig figs. It's a nice pretty number, so we can't really take intermediate decimals or anything like that. Not a problem here. Now we have centimeters cubed, and density is grams per centimeters cubed. So we want to take the amount of grams we have, divide by the amount of centimeters cubed we have, or cubic centimeters that we have, and we would get 1.26 grams per centimeter cubed. This is rounded to the proper sig figs. I should have kept my 0 in the 2.50 liters. That was my mistake. All right. And for the last problem of this video, we're going to go over the challenge problem. So again, it's not going to be verbatim, this problem. It's going to be a cube of some different material with some different density, with some different side length, or I'll give you the mass and ask you to give me the side length, something of that. So the first thing we want to do is we want to check if our units make sense. We have meters and centimeters cubed. Okay, so we're going to have to do a conversion there. So again, we can do conversions in all sorts of ways. This is the way that I presented how to do it. So we're going to start with the volume equation. Side cubed is equal to volume, so we'll plug in the cube of our side. Our side is 5 meters. We cube that. We get 125 meters cubed. We want to convert that to centimeters, or cubic centimeters. So what we have to do is we have to take our centimeter to meter conversion. We dimensionalize it by cubing it. So if we have meters cubed here, we want to have meters cubed here and centimeters cubed here. That'll give us this number at the end of the day. Now, I could have put one more significant figure in there because we are going to round to 4 significant figures at the end of the day, but it wasn't necessary. As long as your note keeping is good to get you the right answer, you'll notice at the end of the day, we have 4 significant figures. So once I have my cubic centimeters, I'm simply going to times my cubic centimeters by my density. So my density, the centimeters cubed, will cancel out, and I'll be left with just grams. I didn't specify what unit I wanted the mass in, so whatever unit you choose is fine. There's no reason to really change from grams into anything else. The important thing was that I said round to 4 significant figures, so we would take our decimal place and just count off, use the last digit after there to estimate, is it rounding up or rounding down. We rounded to 9.843 times 10 to the 8 grams. If you have any questions with this problem or want to see another version of it, just feel free to email me or reach out during office hours. Otherwise, I'll see you in lab this week.